So welcome back. Now we are going to move on, but I would like to do a recap because I like to do recaps, brings everything back to your memory, to your working memory. So we've looked into Boolean retrieval. Boolean retrieval, we simplify the documents by dropping the order, dropping the number of currencies. We just remember whether yes or no a term is in a document. And then we can query in a mathematically perfect way with and, not, or. And we can say whether yes or no a document fulfills a query. And then we return a subset of the collection of documents as the results of the query. Then we saw that in order to do that fast, we have what's called the standard inverted index. And the standard inverted index is based on the left, the terms. So this is what you repeated 500,000. You can think of the number of yellow rectangles like this. And then facing them are postings list. These are non-positional postings because we don't know the positions in there, and every number in there is a document ID. What you have in the purple squares that you cannot see very well is just the size of the list of blue rectangles on the right. It's called the document frequency. It's here for convenience so that you know the size in O of 1 without having to actually measure it. And this is the standard inverted index. Standard because you can actually modify it and tweak it for other M's. And that's exactly what we did with the byword index and the positional index. You can see the byword index and the positional index as variations of the standard inverted index. Is it on strike? Yes. So last time, went too much? Yes. Last time we saw that building the standard inverted index is not trivial at all because you have a lot of complexity along the way. You need to tokenize the document. You even need to decide what a document is. You need to do some linguistic preprocessing by considering the language you have, the conjugation of the words, the cases, the declinations, and so on and so on. So you can group together some words and consider that they are the same, the one and same normalized type, right? And that gives you a term in the standard inverted index. So this is very complex. And finally, you build the index associating a postings list with every term. We saw that there are stop words. The stop words would correspond to the terms where the postings list is absolutely gigantic. In fact, it's almost all the documents. You basically have to imagine there is a million documents in your collection. If you have a stop word like or n or and so on, and you have the doc IDs, it's going to be everything. 1, 2, 3, 4, 5, all the way to a million. So if you want to save some space, you can just drop them, which is what we did back then. But now we have the capacity, so we no longer really consider stop words. But historically, they were here. Then we saw that you can build equivalence classes. I shouldn't have said terms here. I should have said equivalence classes of words. And you get what's called the normalized type, right? So USA, today, window, Zurich, and so on. These are equivalence classes, and you call them normalized types. And every one of these is going to give you a term in your standard inverted index, right? So this is the symmetric case where it's an equivalence relation. And one way to create these equivalence classes is to use a stemmer. So the Porter stemmer is one of them. So you basically put the words through an algorithm that gives you some canonical thing. I don't know what to call it except a thing because these are not words you get on the right. But this gives you the equivalence classes, right? All of the words that give you the same results are considered to be in the same equivalence class. Then we looked at skip pointers, which allow you to have the magic power of jumping quickly through the postings list. And typically, you take the square root of the size of the postings list, so the square root of the purple number that you have on the left, and you can put the skip pointers like that. All right. You will have probably exercises on that, like, for example, how many comparisons will you need with this example of a posting list and this other example if you intersect them? So how many comparisons do you require with or without the skip pointers? Okay. Okay. Now we have the byword indices, what I just presented to you, where instead of the terms, you have pairs of words. You have the positional index where you still have the terms, but then instead of the just the document ID, you have not only the document ID, but also the number of times that the term appears in the document. That would be the bag of words. And if you add also the positions, the exact positions in the document, then you have the list of words. In other words, imagine that you take the latest Dan Brown novel and you tokenize it, you build the index and so on, and you build the positional index. And we don't use any stemmer or anything. We just preserve the original word. Who agrees that you didn't lose information and you can turn it back into the original book? Who sees that? Because you have all the positions. So you can do the same thing in the reverse direction and get it back, right? So it's always important to ask yourself when you see an index like that, what information do you preserve? What information do you lose, right? And depending on what you do, you might lose the order, you might lose the number of occurrences, you might lose the exact terms, you might have equivalence classes and so on. Okay. So now let's move on to more material. So coming back to standard inverted index, this is one that we built last time. We have all of these terms. The purple square is the document frequency, and then we have 1, 2, 3, 4. These are the 4 document IDs. Then we have the place in which they appear. Now, let's look up things. Imagine somebody wants to run a query, and that query is, need to wait until the slide comes. Maybe there's, I don't know, some Bluetooth interference that causes it to be slow. All right. So who thinks that should will be found? If somebody queries for Schultz, raise your hand if you think it will be found. Okay, so you see it, right? And indeed, it can be found. It's actually right here. Now, who thinks that could can be found? Who thinks it cannot be found? How do you know? How could you tell that? It's a big list, right? How are you able to tell that it's not there? Yes? Yeah, exactly. So there's 2 important things in what you said. The first one is that it is sorted. And indeed, that's alphabetically sorted. And the second thing is that you can use a binary search in order to find, to locate the word. Now you're already using the fancy words that we know in computer science. In fact, this is what we teach to kids in primary school, right? It's basically to look up a word in a dictionary. And in fact, we don't tell them it's binary search, but this is what you in fact do when you open a dictionary, right? And try to look up a word. At least in the good old times, because now we are spoiled, we just type the word in a computer, but back then we had to look it up in a dictionary. So yes, indeed, it's sorted, and we can use binary search, and that is going to actually be the focus of our attention today. So indeed, could is not there, and the way you tell is that if you look, if you would do a binary search, you would probably arrive somewhere here, and here you see it between com and fair. Could is not there, so, and it even rhymes. So we know that it's not in there. And by the way, since you mentioned the binary search, indeed, you can locate it. Now, we are human beings, so this is kind of natural to us, right? When we are used to looking up something in an alphabetically sorted list, we are kind of doing a binary search. It's probably some variation of it because we probably have some other additional ways of looking it up, like it's probably a mix of a binary search and of a linear search. We probably roughly locate where it is and go through it. But yes, indeed. But that's something we didn't cover before. I just told you we have the terms, it's sorted and so on, but we didn't actually see how we locate the term. So we have something that is missing in there in order to to locate the posting list corresponding to a term. Now, the binary search, what's the complexity of it? That you all know, right? Who knows the complexity? Okay, say it all at the same time. It is all again, exactly. So this is the complexity of a binary search. Can we do better than that? Are there data structures that are even better than logarithmic? Yes? Exactly, we can use a hash map or a hash table. So for example, to find E. So we can use a hash table, which is an implementation of a map that is called a hash map. So imagine that I have this, it's small, of course, it's bigger than that in reality. So I have this. And what is going to happen is that I have this magical function that's called the hash function that looks a bit random. It just returns some position in there. And then I will put my terms at the position that the hash function tells me, right? And then I can put the posting lists in there. That's basically the same thing. It's still a standard inverted index, except that now I have an additional structure to organize my terms, which is a hash map, right? So this is correct. Now, who took the cryptography course? Some of you, maybe not yet. So hash functions actually come from cryptography. They have some ideal assumptions. For example, they are not reversible or should be very hard to reverse. They should avoid collisions. So if the table is large enough, then it should be unlikely that you are going to have two terms that land in exactly the same position, and so on, right? So there are desirable properties that hash functions have. And if it is the case indeed that there are no collisions, or that there are few collisions, then the complexity of retrieving a term with a hash map is, everybody, O of 1, exactly, it's instant, right? You just compute the hash, and then the lookup in the array is also, with pointers, pointer arithmetics, you can immediately know the position in memory to look at, right? So you take the hash, and there you go. So we have a solution in O of 1, right, now to locate the posting lists. And now you can traverse the posting list, go ahead with the intersection and union algorithm and so on. But there are a few limitations of these structures. It looks good, right? O of 1 is absolutely fantastic. But what is the problem? What are the limitations with that? Some of them. Anybody? In Zoom, maybe? Anybody on Zoom? Nobody? You want me to tell you? Okay. Let me tell you then. Yes?
Cache locality.
Cache locality. Oh, that is a physical consideration. So I'm not very familiar with this one. So is it an implementation optimization? Oh, I think I know. Just had to think. Do you mean that if you cache, so for example, all of these hash map might be on disk and so on, and then you have a cache for the most recent values that you looked up, but since the hash function would give you pretty much random values, then whenever you look for a term, it's at a different location, and so that will be very inefficient with caching. Is that what you meant? Okay, awesome. As we say, I think there's an expression in Swiss German, we say, "Sophie Jabekate," when you take time to understand. Okay, so cache locality, indeed, this is indeed one of the limitations. I don't know if it's on my slide, but you're right. Anybody else? Yes? Duplicates in the sense of collisions that you have, yes, absolutely. So this is an extra complexity. So basically, this is the case where the hash function is not perfect, and you have two terms that end up in the same location. From an implementation perspective, you can still handle it. What you can do is that you have your hash map, and then you have an additional singly linked list, and you can queue you can link together all of the terms that would be in the same cell, right? So then that would be a performance hit. Basically, you would be slightly slower than O of 1. It's O of 1, but a tiny logarithmic component because of that. Yeah. Absolutely. So the hash function is not perfect. Anybody else? Yes? Yes, so this is known as the Fiat constant factor, right? So even though you have one, you might have a constant factor that actually is not worth it, right? So if you have an algorithm that is exponential with a super tiny constant and an algorithm in O of one with an enormous constant, then sometimes, I'm caricaturing, right? But sometimes the more complex algorithm might actually win in practice. Right. So yes, the constant factor plays a role as well. So here's another example. These are very good points that you made. Here's another example. Imagine that you want to query a range. You don't want to just look up term A or term C and so on. You want to look up a range, everything that's between A and C. Who sees that you cannot do this with a hash map? Right. Because in a hash map, what you would need to do is enumerate all of the terms that are between A and C, and then look them up individually. So first, it would take a while, it would take time, but second, you might not know all of them. Imagine that instead of words, these are doubles, like real numbers. And even if it's words, like what are all the words in the dictionary that are between, I don't know, information and I don't know, juncture, like just two words, enumerate all of them. You cannot really do that, right, without the actual dictionary. So we are stuck here. And the problem is that this is an important use case because there are many cases in practice that I will need range queries. And I'm going to even show you some of these use cases today. So this is a limitation of hash tables, that we cannot do this. We would have to manually look them up, assuming we know the list between them. So no support for range queries. Hash function is not perfect in real life. This is basically what some of you have mentioned. And another one is the space requirements. If you want to avoid the collisions and have good performance, the amount of space or disk that you need can be enormous, right? So you need a lot of space for a hash map. So these are some of the limitations. But fortunately, we have invented alternatives to hash maps that might be in complexity less efficient, but in practice, we actually love them. And we are going to come back to binary search that you mentioned. This is exactly the idea. So what I would like to do here, we have a few more minutes, I would like to refresh your memory. I'm assuming you've seen that. Who saw probably in Datenstruktur and algorithms, the notion of tree, binary search tree? Who saw that? Who covered that? Okay, that's great. So I skim over that. It's always good to refresh things. Then you can even tell me if I get something wrong, if it's fresh. So we can have trees like that. So a tree structure is basically made for computer scientists of a root, and then you have children. And at the bottom of the tree, you have the leaves that do not have children, at least if it's a finite tree, which we usually assume in computer science. Now, just so you know, and you probably know, for mathematicians, a tree doesn't have these directed arrows. For a mathematician, a tree is just some graph that doesn't have any cycles, and the root could be anywhere. But for computer scientists, we usually single out one of the roots as one of the nodes as being the root, right? So this is why we have these directed arrows. Then, in terms of definition, we have the concept of the height of a node, like how high is it? It's the number of edges the maximal number of edges that go to one of the leaves. That's 2 in that case. We have the notion of the depth of a node. That's the number of edges that's separated from the roots. We have the notion of the weight of a node, which is the number of descendants it has included itself. In that case, that's 6, right? So yeah, you have a few concepts like this. And then, so that's for a node, but for a tree, you can also consider the height of a tree. Some people also say the depth, but I think that height is probably more precise. So the height of a tree, in that case, would be 3. It's the height of the roots. Okay. So that I assume you all know. Then what is a binary tree? Well, this is when we start restricting the number of children that every node has. And for a binary tree, we say it has to be at most 2, can be 0, can be 1, can be 2, right? And you get something that looks more like this, at most 2 children per node. Okay, so you see at some places there is only 1 child on the right here, for example, and the leaves have 0 children. That is a binary tree. Then there are several kinds of them. You have the notion of complete binary tree, where all of it's basically layer by layer, and then only the highest depth is incomplete, right? And then you fill them left to right. So this is called a complete binary tree when it looks like this. Then you have the notion of a perfect binary tree if it's not only complete, but even the last layer is completely filled. So this is called a perfect binary tree. And now what we are interested in is not just a binary tree, because a binary tree is just the nodes themselves, but if now we add some labels on the nodes of our binary tree, we have what's called a binary search tree. And there is a property that must be fulfilled in the case of a binary search tree, is that there is an order on the labels. So in that case, I take numbers, integers. And what must happen is that if we have 4 in there, then we know that everything on the left is less than 4 and everything on the right is more than 4, right? This is what makes it a search tree. And of course, a binary search tree is just a data structure that supports the binary search, right? This is the goal of what we want to achieve in there. All right, and you see this is true also for 2, for 6. It's always true that you have this property. Now, in our case, we are not going to be using integers because we want to build an index on that contains words. So this is information retrieval. So what we are going to have is terms or words. It is ordered because you have some alphabetical lexicographic ordering of the words. So you can see that this fulfills the search property, right? Who sees that? Okay, you see, because for everybody else, oath starts with an O, and here everything comes alphabetically before oath, and here on the right, everything comes alphabetically after oath, right? So in the same here, port is in between or and 2, can is in between B and not. All right, so this is a binary search tree, and I have words in there, terms. So you see, we are now slowly going in the direction of something that could be useful for our standard inverted index. It is now 11 a.m. So we are going to take a quick break, 15 minutes, and I'll see you at 11:15, and then we'll continue our exploration of trees, and actually B+ trees and B trees, to be more exact. Yeah, see you in 15 minutes. Thank you.